Budzinski. He will talk about random walk on supercritical causal maps.
Okay, so so hello everyone, and thank you very much for the organizers for giving me the opportunity to speak here. So I would like to talk about the simple random walk on causal maps, which are a class of planar maps that are built from trees, but which are still quite far away from having a tree structure. So let me be more precise and define the model right now. We start from an infinite plane tree, T, just like this one, and at each level we add a cycle around the root, which visits all the vertices of the same generation from left to right, just like here. Okay, so I obtain an infinite planar map, which I call the causal map associated to T. And what I'm going to be interested in this talk is the case where the underlying tree here is a supercritical Galton-Watson tree conditioned to survive. Okay, so the infinite graph I obtain is a graph with exponential volume growth that we assume to have that we expect to have some hyperbolicity properties. Okay, so is the model clear for everyone? So maybe before studying some properties of this object, why are we interested in this kind of graphs? So maybe the first reason is that in the critical case, some closely related models have been studied both by theoretical physicists and by mathematicians. So it has been, the reason why it has been considered by physicists in the 80s is that basically the three-dimensional analogues of, say, uniform triangulations or similar graphs do not seem to be very nice in 3 dimensions according to the numerical simulations of the physicists. And from what I understood, the analogues of the causal maps seem to have nicer scaling limit properties. So I think the best person to ask about this kind of questions here is probably Tim. And also the rigorous study of this kind of objects is only very recent. So there is a nice paper by Nicolas, Tom, and Asaf Narmias from last year, which studies both metric and spectral properties of critical causal maps. So the same kind of maps, but where the underlying tree is a critical Galton-Watson tree. Another reason to look at this kind of model is that causal maps are an example of map containing a certain fixed tree, and in some sense it's an extremal example where the map has the topology of the plane, not of a tree, but where the connections are as close as possible. So we can expect that if we prove some bounds for the causal map, then it might be possible to extend these bounds for all the planar maps containing a fixed tree. For example, this kind of idea can be applied in the UAPT to obtain some convergence of geodesics properties. And in the supercritical case, it is also possible to generalize some properties of causal maps to any planar maps containing a supercritical Galton-Watson tree. So it will not be the case of the properties that I will discuss today, but for example, some properties of the geodesics in supercritical causal maps can be generalized like this to a wide class of hyperbolic planar maps, which includes the pshit, which are the natural hyperbolic variants of the UAPT. Okay, another reason to be interested in this kind of graphs is, okay, supercritical Galton-Watson trees have been extensively studied, and we might ask ourselves, for some properties of these trees, is the tree structure necessary or not? And so here the answer will be that the tree structure is not always necessary. And of course, like many models of random graphs, and random planar graphs, it allows to produce some nice pictures. So, for example, here is one. So this is the circle packing of a supercritical causal map with geometric offspring distribution. So here I cheated a little bit. I triangulated the faces before taking the circle packing. And as you can see, it can be packed quite nicely in the unit disk, which is something that we expect in general for graphs with hyperbolic properties. Okay, so today I'm going to focus on the simple random walk on my causal map. The first easy remark that we can make about the simple random walk is that by construction, my causal map contains a supercritical Galton-Watson tree, which is a transient graph. It's a classical result by Lyons from maybe 30 years ago. In particular, the causal map is itself transient, so the random walker will escape from the root to infinity. And the next natural question is how fast will the random walker escape? Okay. And so here is the main result that I wanted to discuss today. Assume that mu of 0 is equal to 0, so the underlying tree has no leaf. I don't believe that this assumption is necessary, but I only managed to prove this result in this case. Then the simple random walk has positive speed, which means that the distance between the random walk and the root vertex grows linearly in n. Okay, so before explaining the ideas of the proof, let me resume basically what is known, or at least sum up some results about positive speed in random hyperbolic graphs. So there are already some models where positive speed is known. Probably the most basic example is supercritical Galton-Watson trees, where this result has been proved by Lyons, Pimentel, and Perez. In particular, in this case, it is even possible to compute explicitly the speed in terms of the offspring distribution. So it has also been proved for the cheat, which are hyperbolic versions of the UIPT, and, for example, for Poisson-Voronoi tessellations of the hyperbolic plane. But these three models all have something in common, which is a stationarity property, which means that the environment around the random walker at time n has basically the same distribution as the environment around the root. So it's exactly true for the last two models, and for the first one, it's not exactly stationary, but the proof of Lyons, Pimentel, and Perez relies on the construction of a stationary environment. And for causal maps, there does not seem to be an easy stationary environment to be built. It seems that for Galton-Watson trees, there is a kind of miracle which allows to construct a simple stationary environment. And okay, I'm not claiming that it's impossible to find one, but there does not seem to be a natural and simple candidate. So to prove positive speed, we need to find new ideas, and the two main ingredients of the proof are the following. First, we need to make sure that the random walk does not get stuck in very bad regions where it would stay for a long time without to go up, which is guaranteed with the help of an exploration method of the causal map. And the second ingredient is more classical. It's a regeneration argument. So we use renewal times, which is a classical tool, for example, in the study of random walk in random environment. Okay, so let me now move on to the details of the proof. I'm not exactly going to work on my model built from one tree. I'm going to focus on a model with a bit more stationarity or translation invariance properties, which is the following. Instead of starting from a single tree, I start from an infinite forest of IID Galton-Watson trees. And by infinite, I mean B infinite, so I have infinitely many trees, both on the left and on the right. And instead of drawing cycles around the root, I draw horizontal lines at each level, just like this. And for some technical reason, I also need to add a parent to all the roots of the trees. So I have some vertices at hit -1. And I will focus on the proof of positive speed towards the top in this half-planar model. But once positive speed is proved here, it's not very difficult to obtain a positive speed in the original model. Basically, if we know that we are moving to the top quickly, it is very hard to make turns to the right and to the left in these very wide trees. So eventually, we will stay in the same tree, and we can do as if there was only one tree. So it's not hard to go from positive speed here to positive speed in one tree, and I will now prove it in this half-planar model. So let's first look at the local drift at each vertex of my graph. Assume that I look at a vertex with I children. Then it has one neighbor on the left, one on the right, one parent in the bottom, and I children on the top. So the local drift at my vertex is equal to I-1 divided by I plus 3. In particular, since all the vertices have at least one child, this local drift is always non-negative, okay, which is very convenient. And moreover, if I have if my vertex has at least two children, then this local drift is positive. In particular, if I assume that mu of 0 is 0 and mu of 1 is 0, then the result is very easy, because I have a positive local drift at every vertex, so the heat will dominate a random walk with positive drift on Z. So what I want to prove is that I spend a lot of time on these nice vertices with at least two children, and I don't get stuck in some regions, in some large regions, where all the vertices have only one child, just like this one. So I define the k-bad vertex as a vertex like this one, V. So it means that V and its first k descendants all have only one child, and the same is true for its k neighbors on the left and its k neighbors on the right. As you can see, it's a very rare properties. More precisely, if I look at a fixed vertex, for V to be k-bad, I need all these k times 2k plus 1 vertices to have only one child. So the probability for V to be k-bad decays very quickly in k, like exponential of minus k squared. So if the probability to be k-bad behaves like exponential of minus k squared, it seems natural to expect that if I visit n vertices, then the worst of all these vertices will be roughly square root of log n bad. But it's not easy, it's not completely obvious, because the vertices visited by the simple random walk do not have to be typical vertices. For example, if I reach some vertices from the top, I have already some partial information about it. So we need to be a bit careful. More precisely, the idea of the proof of this lemma is to explore the causal map at the same time as the random walker. So each time the random walker reaches a new vertex for the first time, we discover this vertex and all its ancestors, because we don't want to discover a vertex and discover its ancestors afterwards. So the explore part will look like something like this. We have discovered some vertices, some other not. But for each vertex that we have discovered all its ancestors. And if now I discover a new vertex V here, it's quite nice because I have a lot of room available on the right and on the top. So the probability for this vertex to be k-bad is bounded by the probability for all the vertices here to have only one child, which is exponential of minus k squared. On the other hand, I still may have a problem if I try to discover this vertex. Because here, I don't have a lot of room on the right. Of course, on the left, everything is already discovered. And on the right, I don't have a lot of room, so I already have maybe a lot of partial information about the right neighbors of this vertex. So this is something I want to avoid, this kind of situation with very narrow pits. So what I do is that every time such a narrow pit is formed, I fill it entirely before it gets too narrow. And if I do that, I have always a lot of room next to the vertices I discover. So at each step, the probability to discover a k-bad vertex is exponential of minus k squared. And it's possible to control the total number of vertices that we need to discover. Of course, it's a bit more than the number of steps of the random walk, but it's something that we can control. Okay, so now I know that the worst vertices I find are basically square root of log n bad, which means that I have always a good vertex, a vertex with at least two children, at a small distance, at distance square root of log n. And I always have, if I have a nice vertex at a small distance, then I have some probability to reach this nice vertex in a very near future, like in a square root of log n steps, by using a path composed of vertices with degree 4, because they have only one child. So the probability to reach a good vertex in a very near future is always at most 1/4 to the square root of log n, which may decay to 0 as n goes to infinity, but very slowly. It decays slower than any polynomial. So this is enough to prove that, at each step, we have a probability n to the minus little of 1 to be on a good vertex. So the number of good vertices that we will visit during time n is n to the 1 minus little of 1. And since all these vertices give me a positive drift towards the top, I will accumulate a drift of n to the 1 minus little of 1. So the heat will behave like n to the 1 minus little of 1. So this is not positive speed, but it's not too far away. Positive speed would be constant times n, and we are not there yet, but we're getting close. And when we do this kind of computations in a quantitative way, we can also show that the heat is almost linear and is also almost increasing, which means that when we reach some heat, we will never go way below this heat after. Okay. Now, let me move to the second important ingredient of the proof, which are regeneration times. So as I say that a time n is a regeneration time if it satisfies those two conditions. The first one means that at time n, my walker discovers some new heat for the first time. And the second means that after time n, I will never go below this heat after. So for example, here, I have a causal map with a trajectory of a simple random walk. I have two regeneration times, here and here. For example, here I reach hit 2 for the first time, and I never go below to hit 1 after. This is not a regeneration time because I reach hit 4, but then I go back to hit 3 a few steps after. And these regeneration times are not stopping times, but they still satisfy a sort of Markov property which makes them very useful, for example, in the study of random walks in random environments or in this model. More precisely, they allow me to decompose my my map and my walk trajectory into blocks in a vertical way. And it happens that these blocks are independent and almost IID. Only the first block has a slightly different distribution. Okay, so I have IID blocks, so I can apply the law of large numbers to the IID blocks, and it proves that the random walk has a speed, and this speed is the average heat of a block divided by the average time that we spend in one block. So the only thing left to do is to prove that, that this is positive, which is equivalent to proving that the expectation of the regeneration times are finite. And basically, it can be proved with the help of these quasi-positive speed estimates. So roughly speaking, the idea is that since I have this quasi-positive speed, I reach new heats for the first time quite often. And since the heat is almost increasing, every time I reach a new heat, I know very quickly in a short number of steps if this is a regeneration time or not. And if it's not, then shortly afterwards I will reach some new heat and I can go on like that. And it's enough to prove that these regeneration times have a subpolynomial tail, so finite expectation. Okay. So this is basically the proof of this result. So there are some natural questions that we might ask. For example, I don't believe that the assumption mu of 0 is equal to 0 is necessary, but I mean, this proof is highly non-robust because it's important that there is no vertex with a negative drift. And there are other questions about the random walk that might be asked, like the heat kernel decay or the study of the lambda biased random walk, or things like that. Okay, so I think I will stop here. Thank you very much. Yeah.
The hypothesis H0 equals 0, you use because you use really that when you have a trap, you still not such in a bad environment, right? It's like you use this estimate, and the fact if 0, then you really use that in the trap you still move, right? If I understand correctly.
Yeah, I mean it means that there are some vertices with a positive drift and some vertices with no drift.
This trap, there is part of square, like right? They still contain a bit of square, like.
Actually, I only need to bound the size of the traps, but there is no point in the proof where I need to bound the time spent in a trap. It's just. I mean, the point where it's very important is here, because I say I visit n to the 1 minus little of 1 good vertices, and there is so they give me a drift of n to the 1 minus little of 1. But if I had some very bad vertices with no child, then all these vertices would give me a negative drift, and this might cancel out this, and I would not get something positive.
Yeah.
If there are no more questions, let's hang it from again.
Okay.